Hi, folks. This time we're going to talk a little bit about buffers. Now, buffers in pH solutions are essential to help maintain a very small pH range. And this is very important in biological systems, the human body, blood specifically. Your skin, hair, skin, nails has a preferred pH range. Your urine, soil, aquatic systems, lakes, streams, oceans, and many other locales. The range of pH so that animals, organisms, or parts of your body are healthy and well have very unique and narrow ranges where those pH levels have to be. And they can be thrown off incredibly easily. And buffers chemically help maintain those narrow pH range. Now, in a typical solution, it is very easy to change the pH of a situation. So if we look at an example, let's say I had a 1,000 milliliter beaker and it was full of water, and I added just 0.01 mole of hydrochloric acid. Now, pure water has a pH of 7. If I added a very small quantity of hydrochloric acid, those ions would completely dissociate, and the pH inside of my beaker would very quickly change from a 7 to a 2. So the addition of a small amount of acid would result in a huge, big change in pH. Now, the problem with that is that if this would happen to your fish in your fish tank or inside your body, it could lead to death. So let's go through a couple examples. pH blood levels are very vital that we keep within the range of 7.35 to 7.45. That's a nice normal pH. And the simple act of respiration, when you do excessive exercise or you exercise, part of metabolism is you produce carbon dioxide. Well, that carbon dioxide can mix with water, produce carbonic acid. Carbonic acid is what gets mixed with water to make club soda, which is the carbonic acid in soda pop. Carbonic acid can have a pH of 3 or 4 very, very easily. Well, it doesn't take very much of this to accumulate in a person's bloodstream just by carbon dioxide produced through respiration, and you can throw your body into a state of acidosis. So the body has to use buffers in order to help maintain that normal pH. Your fish. I don't know about you, but through our lifetime, we have had fish tanks on and off for many, many years. And you bring your lovely little fish home in a bag, you have your fish tank, and sometimes they live and sometimes they don't live. People who know what they're doing with their fish tanks check and make sure that the oxygen levels are good. Check also to make sure that the pH is right, because it's constantly changing. Your goldfish are living in here. They're also pooping in there, and their waste is changing the pH of the solution. It is a constantly changing and evolving environment. Well, you take these brand new fish and they're being thrown into a strange, weird environment. And that's one of the reasons it's hard to keep fish unless you are very careful and know exactly what you're doing. You're throwing them into a state where their normal pH levels are thrown all off and they can die. A little aside here, in one of our other talks about indicators, we talked about bromothiamyl blue, and bromothiamyl blue is a great indicator right across that neutral pH range. And if you look at this, which is a common indicator used around fish tanks, bromothiamyl blue is one of those indicators commonly used in that situation. Now, in a buffered solution, and put a little star by this because this is a definition you need to know. A buffered solution is one that resists a change in pH, even when a strong acid or a strong base is added. So a buffered solution is one that resists a change in pH, even when a strong acid or base is added. And this is definitely necessary to maintain those narrow pH levels that are required to keep you and I healthy. Now, without a buffer, if a small amount of acid or base is added to a solution, you get a big change in pH. In this illustration over here, we've got a beaker of plain water, and it has a pH of 7. If hydronium ions, an acid, is added, the pH drastically falls, and you get a low pH in a very acidic solution. If a base is added and hydroxide ions are added, you end up with a very basic solution and a very high pH. But if you add a buffer, now remember, buffers resist changes in pH. That's what a buffer does. If you have a water and buffer solution, what that buffer does is when you add the acid and you add those hydroniums, instead of the pH going low and you get a high acidic environment, yeah, the pH might change some, but it won't drastically fall. And so it goes a little bit acidic and you get a slight change, but not the drastic change. If you have a buffer in this solution and you add a base, what's going to happen is it's going to change somewhat, but again, not the massive change that you're going to see without the buffer. So buffers resist changes in pH. They help maintain that nice status quo. Before we can really explain how a buffer works, we have to remember some of the things that we've talked about in the past. Let's talk about strong or weak acids and bases. Now, a strong acid or base is one that completely ionizes in solution. Remember that you can have molecules, you put them in a solution. If it is a strong acid or base, it's going to completely dissociate. So this is going to completely create ions, lots of hydroniums, lots of chlorine ions. In the dance of the ions back and forth, it's a one-way affair. And if Mickey's is going to be sock hopping with Donald and Mickey, the reaction's only going in one direction. She's going to end up true love with Mickey Mouse, and poor Donald's going to end up with a sad face because he is not going to get the girl. In a weak acid or base situation, there's only slight dissociation. What that means is that the reaction is going to go in both directions. So this compound is slightly going to break into ions, and then it's going to come back the other direction, and then it's going to go break into ions, and then it's going to come back the other direction. It's like going to the sock hop. And Minnie is dancing with Donald, and then she's dancing with Mickey, and then she goes back dancing with Donald. It goes back and forth and back and forth. Some weak acids, the reactions favor the reactant. Some weak acids, it's almost 50-50, meaning that maybe 50% of the time, there's one combination and the other. So it all depends on the specific chemicals you have in those weak acids and bases. Now, why are we talking about this? We're talking about this because when you're dealing with a buffer, buffers always use these weak acids and bases, and they work best when you have this sort of 50-50 relationship, or darn close, where they're kind of sharing part of the time the reaction lives on this side and part of the time on that side, and it's this constant dance back and forth. Another thing that we've talked about in the past that we need to recall is the Bronsted-Lowry definition of an acid and a base. In a Bronsted-Lowry definition of an acid and a base, you get a conjugate acid and a conjugate base that's created with every acid and a base. So what that means is when you have a buffered solution, the buffer is going to have let me read this so I make sure I don't say something silly. The solution is going to be buffered by the presence of a weak acid and its conjugate base. So you're going to have that weak acid and its conjugate base. Both of those are important in making that buffered solution. Or you can have the complete opposite. It is possible to have a buffered solution made of a weak base and its conjugate acid. So you've got an acid that breaks up into a conjugate base and a base that breaks up into a conjugate acid. So let's go through a specific example of a buffer and let's talk through how it would work. Earlier, we talked about a liter of water. We added a little hydrochloric acid, and the pH of the liter of water changed from 7, and then we added the acid, and it changed to a pH of 2. But what if we add a buffer? And the weak buffer we're going to add, or excuse me, the buffer we're going to add is a weak acid, acetic acid. Now, acetic acid is commonly, you consume small amounts of it when you drink vinegar or pickled things like pickles. If we have acetic acid and its conjugate base, its salt, which is sodium acetate, you end up with a reaction that looks like this. So here's our acetic acid, and here is its conjugate base, sodium acetate. So here's my acid, and here is its conjugate base, sodium acetate. The acetic acid, when you put it into this solution, and this is going to be a solution of water plus hydrochloric acid, this little hydrochloric acid we've put in here, it's going to associate almost equal concentrations, about a 50-50 amount of the time of being in the acetic acid situation, and about 50% of the time in the sodium acetate situation. So it's going to be partially over here and partially over there, because some chemical reactions go one way and some are reversible. And this is one of those that's very reversible back and forth. So we use it as a buffer quite often. So if you add this as a buffer into our solution, here's what happens. When small amounts of the strong hydrochloric acid get added to our mixture of water plus our acetic acid, what happens is this. The strong acid is going to bond with the strong acid hydrogen ions are going to bond with our acetate ions here. What they're going to do, because remember, hydrochloric acid, very, very strong acid. So when we put this into our solution, our strong acid, this is going to break up into hydrogen ions and chlorine ions. The strong hydrogen ions are going to bond with our acetate ions. And what does it make? It makes acetic acid. So it goes back and it forms the beginning of the reaction. Well, what does the acetic acid make? The acetic acid makes more hydroniums. And this whole thing, it's kind of like a balance, and it constantly, the more acid you put in, the more it goes to this side. And then the more of this you put in, the more it pops over to that side. This chemical reaction is designed by nature. Humans didn't design it, but this chemical reaction is designed to maintain the equilibrium of the situation. So the more of the strong acid you put in, the more hydrogens bond with the acetate to make more acetic acid, which makes more hydroniums, and it just keeps bouncing back and forth and back and forth. And by this constant balancing act, it maintains the equilibrium of the situation, and it tends to keep the pH exactly the same. Without the buffer in this solution, when we added the hydrochloric acid, the pH changed from a 7 to a 2. When we added the buffer, because the buffer itself has some pH to it, the pH changed from a 4.74 to a 4.6. It changed by a very, very small change in pH when the strong acid was added from the original solution to the final solution. And that's what buffers do. They keep things in a narrow range. So here are the characteristics that make up a buffer. Put a little star by this. This is an important slide of lots of good stuff sort of summed up. In a buffer, the solution is going to contain a weak acid, and it's going to contain its conjugate base. Secondly, the buffer is going to resist any change in pH. That's the definition of a buffer. It resists changes in pH by reacting with any added hydrogen or hydroxide ions. And thirdly, Any added hydronium or hydrogen ions are going to react with the base. Any added hydroxide ions are going to react with the acid. And the result is it's going to resist that change. So these are the things that make a buffer a buffer. It constantly is going to react with whatever you put into the solution to keep the pH the same. Now, if you have a buffer in a solution, it's going to have a capacity. And that's a word that's used often, is what is the capacity of a buffer. And the buffer can only absorb a maximum amount of a strong acid or a strong base until all of the buffering agent has been used up. It's a chemical, and once it's been reacted, it can no longer absorb that excess acid or base. And this is a buffering curve. Here's the acetic acid that was used as a buffer, and more and more strong base was added to a solution. And this is pH on this side, using acetic acid, which is the active ingredient or the acidic ingredient in vinegar. The pH almost didn't change. It stayed pretty much constant for a very large volume of lye a lye solution that was added to this situation. Over a very wide range, it kept that pH exactly the same until it got to the point where the buffer was used up. And when the buffer was used up, then the pH just goes crazy and it rises tremendously. So in any buffering situation, there's going to be a capacity, and it will depend upon the amount of buffer that you actually have. All right, that is the short and sweet about buffer. It's just a big overview, and that will finish us up. You have